Students, today what we're going to do is look at a molecule with two stereocenters in it. Up until now I've been dealing with some videos where you're able to take a molecule with one chiral center and then be able to determine whether that molecule is either R or S based on the four substituents around that chiral carbon. And what you would have seen is that you assign priorities to the four different groups, and you point the lowest priority group away from you, and then you determine the stereochemistry based on the other three groups. That is whether they are arranged in a clockwise direction or anti-clockwise direction, and you name that as S and R. Today we're going to look at a molecule with two chiral centers and try to maybe analyze that particular molecule and see how that differs from a molecule with one chiral center. So what I'm going to do now is draw a molecule with two chiral centers and be able to discuss that with you slightly. So I'm going to start by the molecule 3-chlorobutane 2-or. So if you look at 3-chlorobutane 2-or, let's zoom this a bit. And we can start drawing that. 3-chlorobutane 2-or has two carbon atoms in the center and two on the periphery, and I'm going to draw a methyl group on this side and another methyl group that side. To this carbon I have one group pointing away from me and the other group pointing toward me, and here I have one group pointing away from me and the other group pointing toward me. So if I call that 1, 2, 3, then I would say 3-chloro, and I'm just going to arbitrarily choose the chloro to be at that position and not that position. And then 2-ol, so the hydroxy group I'm going to choose to be at that position, and then put the hydrogens at the remaining positions in order to complete the molecule. So this is the structure of 3-chlorobutane 2-ol. And the next thing I'm going to do is draw a mirror image of the structure. So if I draw a mirror image of the structure, I'm going to start with the group that's closest to the mirror, and that's going to appear closest in the mirror. So that's my carbon, and if I look at the group pointing away from me, it's still away from me in the mirror. Now that's pointing toward me, still toward me, but in the mirror, and I have the methyl group in the plane. I'll draw the backbone of the other carbon and the methyl group furthest from the mirror. I'm pointing in the same direction, is in the same plane. I have one group that's away from me. The hydroxy will still be away from me, furthest from the mirror, and the hydrogen still toward me. So what I've actually done by taking a mirror image of this in this molecule, I've drawn an enantiomer of this molecule. So what we can expect then is that every chiral center, and here I have two chiral centers, this one and this one, that these two chiral centers will change because I put it into the mirror. So what I'm going to do now, I'm going to try to attempt to name this molecule, and I'm going to choose this center first, and remember that this was carbon number 2, that was carbon number 3. So what I'm going to start to do is look at carbon number 2, and I have my lowest priority group pointing toward me, but that hydrogen actually needs to be pointing away from me. So what I have to do then is put the hydrogen away from me and the hydroxy group toward me, and remember that I've switched that around. And then I look at the remaining groups. I have a hydroxy, which is priority number 1. This carbon with the chlorine is priority number 2, and that's priority number 3. Now if I go from the hydroxy to the carbon with the chlorine to the methyl, I'm actually going in an anti-clockwise direction. And since I'm going in an anti-clockwise direction, it would have been S. But since I switched them around, it's now going to be the opposite of S, which is R. So my 2 position is going to be 2R. Now remember, I swap them around, so now I can swap them back. And I had hydrogen and hydroxy there originally. So that 2 position is 2R. Let's do the same thing and determine the stereochemistry at the 3 position. And what I would start off by doing is putting the lowest priority group away from me. So put the hydrogen there and the chlorine there. And do exactly the same thing. Chlorine would take first priority. It has the highest atomic number, so that would take priority number 1. And then go to the next group, which has a carbon with an oxygen in it. That would be priority number 2, since both the carbons are equal, but now this has an oxygen bonded to the carbon atom, so it would make it a higher priority over the carbon with 3 hydrogens. So priority number 1 to priority number 2 to priority number 3, and going again in an anti-clockwise direction, which would normally be S, but since I've swapped them around, it would now be R. So I need to remember that I've swapped them around and swapped them back. So what I have now is a 2R, 3R situation. And in this 2R, 3R situation, I've taken that molecule, converted that to a mirror image, which means now that if you look at the mirror image, this is now carbon number 3, that's now carbon number 2. And because I've taken a mirror image, each of these stereochemistries are going to change. So this will now be 2S, 3S. So the fact that they are enantiomers, I would have to change each of the chiral centers to the other. So those are 2 stereoisomers of 3-chlorobutene 2-ol, and more specifically, these are enantiomers. I'm then going to take this particular molecule, and I'll draw the backbone of this molecule the same as the top. And with this backbone, what I'm now going to do is keep one of the centers exactly the same. I'll choose to keep center number 2 exactly the same. So which means I have a hydroxy group pointing away from me. I have a hydrogen pointing toward me. But on carbon number 3, I'm going to swap my chlorine and hydrogen around. So I initially have chlorine pointing away from me. I'm now going to point it toward me. I have hydrogen pointing toward me. I'm now going to point it away from me. By doing this, I can now name the molecule as ROS at C2 and C3 just by looking at this particular structure. If I look at the 2 position, you'll see that I didn't change anything around the groups at C2. So the 2 position will still be 2R. However, at the 3 position, I swapped 2 groups around. I swapped chlorine and hydrogen around. And you recall that I said whenever you swap 2 groups around, then the stereochemistry changes and R becomes S or S becomes R. In this case, R now becomes S. So I've made another stereoisomer of this particular one. It's not an enantiomer because this is not a mirror image of that, but it is a stereoisomer of that. I'll tell you what it is just now, but before I do that, I'm going to take a mirror image of this new molecule that I just drew. I'll start off by drawing the backbone. draw the hydrogen pointing away from me, chlorine pointing toward me and out of the plane, and on the far side of the mirror the hydroxy group is pointing away from me, and I have the hydrogen pointing toward me. And since I've now drawn a mirror image of this molecule here, I can now take each of these stereochemical centers and swap them around. R becomes S and S becomes R. So that's my 2 position, that's my 3 position. So I had 2R, it's now going to be 2S. I had 3S, it's now going to be 3R. So I have 2 new molecules, and each of these, this pair here that I just drew, is an enantiomer, or a pair of enantiomers. So I have 2 pairs of enantiomers, a pair on the top and a pair at the bottom, and each of these, both the chiral centers are swapped around. 2R becomes 2S, 3R becomes 3S, 2R 2S, and 3S 3R. 4 different molecules. So we can say, if I label them as 1, 2, 3, and 4, I can now say that 1 and 2 are enantiomers. I can also say that 3 and 4 are enantiomers. However, 1 and 3 are not enantiomers. They're different, because remember, this chiral center is the same, but that is different. In that case, we call 1 and 3 diastereomers. One and 4 we also call diastereomers, as would be 2 and 3, and 2 and 4. So all of these are pairs of diastereomers. And what that actually means is that a pair of enantiomers is equal in every respect, physical properties, with the same melting point, the same boiling point, etc., but they differ in the way they rotate the plane of polarized light. So one might rotate the plane of polarized light to the right, and the other might rotate the plane of polarized light to the left with an equal angle. Here, diastereomers are different in all respects. So they have different melting points, different boiling points, the different ways in which they rotate the plane of polarized light. There might even be different colors. One might be crystalline, one might be amorphous. So they're different in all respects. So in a molecule with 2 chiral centers, we get 2 to the 2 isomers, which is 4 isomers, which we have just drawn. These 4 stereoisomers. 2 pairs will be enantiomers, and we'll get 1, 2, 3, 4 pairs which are diastereomers. I hope you enjoyed learning about diastereomers and molecules with 2 chiral centers.